One part of the ice down there, for example, at the moment is moving east, and the ice up there is moving west, and we're in the shear zone at the moment. It's very hard to see that, but actually we are moving, standing right here, right now.
We're literally like Chilly Willy sitting on his bathtub, and the flow we're on is pretty safe, and everything else can, except for the runway. If the runway goes, we're in trouble, but everything else around us can completely fall apart and we can record it.
Right now there's massive changes in the Arctic. There's projected to be very little summer sea ice by 2040 by several global climate models, and the likely reason for that is just straight the ocean and the atmosphere are getting warmer, and so for thermodynamic reasons there'll be less sea ice. However, sea ice dynamics also plays a big part, so we're interested in what's called the mass balance of the Arctic, which is influenced by the growth and melting of sea ice as well as its movement, and so this particular field trip is all to do with the movement of sea ice. This isn't a new question. This has been investigated for 30 or 40 years in all anger, but right now we're lucky. In the last 10-15 years we've had access to GPS buoys. We've got a lot of better equipment than people had previously, so we're getting down to very, very fine scale features in sea ice dynamics.
The idea behind this is we're trying to line up all of the ice thickness data sets so that we can intercompare them.
What we're trying to do is put a bunch of little points everywhere we can to measure the different pieces, and then put it together like a giant three-dimensional jigsaw puzzle. And it's tricky though, because some of the jigsaw puzzle's water, some of it's ice, and some of it's air. And that's a pretty difficult puzzle to put together.
This is an electromagnetic induction antenna, and the idea is that the conductivity at the bottom of the ice cover is different than the conductivity in the water column, and so it can measure when it hits that difference, and from that you get the thickness of the ice cover.
We're trying to measure snow density, so we have a cylinder that we've stuck into the snow, and we know the diameter of the cylinder and how deep the snow is, so from that we can work out the volume of snow. We then take the snow back to the control room and we can weigh how much snow we have, and from that, if we divide the weight by the volume, then we have the snow density.
You're wanting to know whether that volume is getting smaller because of the increased temperature. I mean, ice is really a good indicator of that particular thing, because ice that we're on right now is close to its melting point, so a little bit of change in temperature will either cause it to get thinner if it's getting warmer, or thicker if it's getting colder. So we're trying to use this as somewhat as a bellwether, if you will, of what's going on with the climate.
The trick is to be out here for long hours, not sweat too much, not get too cold, and still get all the work done. Scientists are working on a grid collecting snow samples to do ground truthing with the satellites.
When we ground truth measurement, what we're doing is looking at our measurement that our satellite makes in space, and then taking measurements on the ground over which the satellite is passing to check that what we see from space is representative of what we see on the ground. The satellite sees huge areas of this ice, and it helps me to visualise a bit more what the satellite's actually measuring. It helps me to think of kind of experiments that we could do to learn about what the satellite's actually measuring. So it's very, very useful for me.
We're diving for a couple of reasons. The first today is what we call a familiarization dive. Just acclimates our divers to the polar environment, and then we're going to start our working dives, which will be to carry instrumentation under the ice to basically map the depth of ice keels, the ice blocks that form after a lead opens up and closes again.
big blocks of ice sticking down, keels hanging out everywhere. It was an amazing place to be.
Oh, the keel was out of this world. The light was great. So a few ctenophores up close, lots of ice crystals like you're in a snow globe. It was pretty wild.
For the most part, it went really well. All the divers went in safe. They all came out safe. So we're pretty happy.
I think we're all extremely excited to look at the comparison of the different data sets because we haven't had the luxury of having all these instruments here at one time. But that was one of the points of the proposal.
APLIS base, this is party 2. We're at our sampling site, just checking in. So we're looking at ozone, which is a gas in the atmosphere. And ozone's normally pretty high in the atmosphere, but during special chemistry that happens in the spring, ozone goes to low levels. And when that happens, mercury comes out of the atmosphere and gets put into the snowpack.
It's been found that very high numbers of the native people in some Canadian locations have very high levels of mercury in their systems, to the point where it can create nervous tissue damage in fetuses, and this is because they're feeding on a lot of the local foods by hunting seals and whales, etc. And also it affects the animals in the area, such as polar bears, the high trophic level organisms. They've been found to have some nervous tissue damage, and the mercury accumulates in their livers and really has a negative effect on their health and their livelihood. So that's the real motivation behind understanding the mechanism behind this mercury. So if we can understand this process, then we can understand more about how the mercury is getting into the ecosystem and into the people and into the animals.
We have a really ambitious project, and I was expecting that we wouldn't be able to do half of it because of the time limits at the camp, and we're actually halfway through the camp and more than halfway through our data collection.
We take advantage of any opportunity we can to put the buoys out because compared to other places in the world, there isn't a lot of information coming back from the Arctic about the different environmental conditions. So we try to get as much information as possible. Unfortunately, it's a really remote area, and so you don't get here very often, and it costs a lot to get here. So there's a lot of coordination that goes on to share the information so that we can get the best set of observation possible and make the best predictions that we can about what's going on in the Arctic.